Exponential functions. What is an exponential function? An exponential function is in the form y equals a times b to the x, where a is a non-zero constant, b is greater than 0 and not equal to 1, and x is a real number. And then we have some examples. Y equals 0.5 times 2 to the x, and f of x equals negative 2 times 0.5 to the x power. So first we're asked to evaluate a function, an exponential function. We have y equals 5 to the x power, and then we have a list of x's, our inputs or our domain of 2, 3, and 4. And then we can make a table and look at some values with this. So we have x as our input or our domain, and then we have our exponential function, y equals 5 to the x, and then we have our output or our y. So if we put 2 in for the x value, we'd have 5 to the second power, which is 25. So when x was 2 as the input, the output is 25. Then if I look at the second number we're given, an x of 3, I have 5 to the third power. 5 times 5 is 25, times 5, 125. So my output or my y value is 125. Then 5 to the fourth power. 5 times 5 times 5 times 5, 625. So when my input or my x was 4, my output or my y value is 625. And we can see how quickly these grew. We have the x value is only changing by 1, but these y values are changing exponentially. They're growing super fast. Let's take a look at a new one. In function notation, we have 2 to the n, t of n equals 4 times 3 to the nth power for the domain of negative 3 and 6. So if our domains are negative 3 and 6, that just means they want us to put in negative 3 and 6 in for the n and solve. So t to the negative 3 means we put in 4 times, and where the n is, we put in negative 3. Well, the law of negative exponents says 3 to the negative third power would be equal to 1 over 3 to the third. Well, 1 over 3 to the third, 1 over 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So 3 to the negative 3 is equal to 1 over 27, and then times 4. So that gives us 4 27ths. So when our input or our n is negative 3, our output or our t of n is 4 27ths. Then we could do t of 6. We put 6 in for our n. So we have 4 times 3 to the 6. Calculator's super handy. We could do 3 to the 6th power to get 729. 4 times 729, 2,916. So when our input or our n is 6, our output or t of n, 2,916. All right, so let's go through and take a look at these. We have evaluate each exponential function for the domains of negative 2, 0, and 3. And then we have 3 different functions. We have y equals 4 to the x power. We have f of x equals 10 times 5 to the x. And we have g of x equals negative 2 times 3 to the x power. So first we go through and put in negative 2. So I have 4 to the negative 2 power, which would be 1 over 4 squared, which is 1/16. Then 4 to the 0 power. Anything to the 0 power is just 1. Then I could do 4 to the third. 4 times 4 times 4 is 64. So when my domain is negative 2, 0, and 3, with this function, my output or my range, my y values, 1/16, 1, and 64. Then we'll do the same thing on the next one. 5 to the negative 2 power, we put negative 2 in for the x. Law of negative exponents says that's 1 over 5 squared times 10 is going to give us 2/5. We put 0 in. 5 to the 0 power is 1. 1 times 10 is 10. Then I put in 3 to the 5 to the third power. 5 times 5 times 5 times 10, 1,250. Gives me my list of my range, my output, or my y values. Then I can do the same thing with g of x. Negative 2 times 3 to the negative 2 power. 3 to the negative 2 becomes 1 over 3 squared, or 1 over 9 times negative 2. Gives us an output of negative 2/9. Then 3 to the 0 is 1. 1 times negative 2 is negative 2. And 3 to the third, 3 times 3 times 3 is 27 times negative 2, negative 54. All right, great word problem example here for using exponential functions. Suppose 20 rabbits are taken to an island. The rabbit population then triples every half year. The function f of x equals 20 times 3 to the x, where x is the number of half-year periods, models the situation. How many rabbits would there be after 2 years? This is a great function. It shows us some great parts here because we have triples, is why we have a 3 here. We start with 20 rabbits, is why we have a 20 here. And the x is the number of cycles, or the number of times it triples. While we're told in the word problem it triples every half year for 2 years. Well, if it's tripling every half year for 2 years, it's tripled 4 times. So the value that's going to go in for the x is going to be 4 because we had 4 cycles or 4 different frequencies of tripling. So f of 4 would be 20 times 3 to the 4th. 3 to the 4th is 81. 20 times 81, 1,620. That's a lot of rabbits. So after 2 years, there would be 1,620 rabbits. All right, I think you guys are ready to try one on your own. You guys try this one. Suppose there are 10 animals taken to an island and the population of these animals quadruples every year. Use the function f of x equals 10 times 4 to the x. How many animals will there be after 6 years? Pause the video here. Let's see how you did. All right, so in this case, the 6 years is our number of cycles, our number of frequencies that it's quadrupling. So we're going to put in 6 for the x value, and we'll have 4 to the 6 times 10, and we get 40,960 animals. So here are 2 graphs that show what exponential functions generally look like. To graph an exponential function, make a table of values, plot the points, and then join the points to form a smooth curve. So the blue one from left to right, it's growing very quickly. This would be exponential growth. And the red line from left to right is showing exponential decay. It's getting smaller and smaller and smaller and closer to 0 without actually getting down to 0. So let's try some tables. We have f of x equals 2 to the x power, and we're going to make a table of values. So we're going to do 2 to the 0. Anything to the 0 power is 1. 2 to the 1 power is 2. 2 squared is 4. 2 to the negative 1 would be 1 over 2 to the first power using the law of negative exponents. We get 1/2. And 2 to the negative 2 would be 1 over 2 squared, or 1/4. Then we can see that these quickly get off the graph. We have a point at 0, 1. We have a point at 1, 2. We have a point at 2, 4, and then it's quickly growing. And then on the other side, at negative 1, we're halfway between 0 and 1. Then at negative 2, we're at 1/4, and our numbers are getting smaller and smaller and smaller as we go out. So we have this from left to right, it's showing exponential growth. Now you can see how hard these are to graph because we got to find points because they quickly get off the graph. Find points around the origin that'll show us using a table of values. All right, let's take a look at another one. We have f of x equals 1/3 to the x power, and we're going to complete this table. Anything to the 1 power is just itself, 1/3. 1/3 squared is 1 times 1, and 3 times 3 gives us 1/9. Anything to the 0 power is 1. And when we have an exponent of negative 1, that gives us the reciprocal or the inverse. So the inverse or reciprocal of 1/3 is 3 over 1, or 3. And then we can apply a negative 2 as an exponent and get 9. Then we go to fit that on our graph, and we can see at 0, 1. At 2, we're way down, close to 1/9. At 1, we were at 1/3. At negative 1, we're up here at 3. And negative 2, we are way off our graph. So you can see how quickly these grow or decay. And if I look at this from left to right, it's getting smaller and smaller and smaller. So this is a graph of exponential decay. All right, you guys pause the video here, try this one. All right, welcome back. I'm running out of time, so we'll go quick here. Our tables will be 1/16, 1/4, 1, 4, and 16, and the graph will look like that. And that should get you guys started on exponential functions. OUT spells out.